Hi, welcome to Algebra 2 Common Core. In today's lesson, we're going to expand on the Pythagorean identity that we learned back in lesson number 4. We're going to see that we can actually use the Pythagorean identities to include all 6 of the trigonometric functions. Just remember that in math, an identity is an equation that is always true. So no matter what values I put in for the variable, it's going to be a true statement. Identities can help us to make replacements so that we can simplify trigonometric expressions. So recall in our unit circle how because I can draw a right triangle and I see my x-coordinate and my y-coordinate, I know then that by the Pythagorean theorem, x squared plus y squared is equal to 1. In our unit circle, we know that for any angle, x represents the cosine of that angle, and y represents the sine of that angle. So I can replace x with cosine, so I would have cosine of theta squared, plus I can replace y with sine, so I'd have sine of theta squared is equal to 1. So this is our first Pythagorean identity, and we've been using this Pythagorean identity since lesson 4 in this unit. Today we're going to expand on this Pythagorean identity and see how we can use it with all 6 of the trig functions. So take a look at the first box in your notes. It says, what happens if you divide each term in the Pythagorean identity by cosine squared theta? So I'm starting with my original Pythagorean identity, cosine squared plus sine squared equals 1. Now just a note about notation here. When I write cosine squared theta, that's exactly the same as saying the cosine of theta squared. So it's how I show that the cosine function is being squared. So I'm going to go through and I'm going to divide each and every term by cosine squared theta, or the cosine of theta squared, however you prefer to write it. So I'm dividing the first term by cosine of theta squared, the second term by cosine of theta squared, and the third term. So theoretically, if I do the same thing to all 3 terms in an equation, I should preserve equality. Now in the case of the first term, when I divide cosine squared theta divided by cosine squared theta, that's just giving me an answer of 1. It's the same term divided by itself. Now look at what happens with my second term. I've got sine of theta squared divided by cosine of theta squared. We should recognize the ratio sine theta divided by cosine theta. That's really just equal to tangent of theta. Since both of them are squared, I'm going to say tangent of theta squared. Now on the right side of the equation, 1 divided by cosine, we should recognize that as one of our reciprocal identities. 1 divided by cosine is secant, so 1 divided by cosine squared should be the secant of theta squared. So here we have our second Pythagorean identity. 1 plus tangent theta squared equals secant theta squared. Let's go to the second box. It says, what happens if we take each term in the Pythagorean identity and this time divide it by sine squared theta? So again, I'm going back to my original Pythagorean identity, and this time I'm going to divide each and every term by sine of theta squared, or sine squared theta. Doing the same thing to all 3 terms in my identity should preserve equality. So in the case of the first term, cosine theta divided by sine theta should be cotangent. Since they're both squared, I'm going to say cotangent theta squared. Plus, sine theta squared divided by sine theta squared is 1. And 1 divided by sine of theta is cosecant of theta. And again, since it's squared, I'm going to say cosecant of theta squared. So these are the 3 Pythagorean identities that I'm going to be using in this lesson and for the rest of this unit. So just for some easy practice on how this works with the Pythagorean identities, let's look at example number 1 at the bottom of the page. It says sine squared of something plus cosine squared of 75 degrees is equal to 1. Well, in order for this to be an identity, my angles have to match. So I would have to fill in a 75 degrees here so that sine squared of 75 plus cosine squared of 75 is equal to 1. For B, I've got 1 plus cotangent squared of something is equal to cosecant squared of 18. So the only angle that's going to make this true is 18 degrees because the angles have to match in my Pythagorean identities. In C, sine squared of 64 degrees would have to have a cosine squared of 64 degrees as well, so that when I add those together I would equal 1. Now again, you could check this on our calculator because I do have a sine button on my calculator and I do have a cosine. If I'm going to put this into my calculator, I would have to enter it this way. Parentheses, sine of 64, close the angle, and then square it. Plus cosine of 64, and again, parentheses around the angle and the function, and square that, and check to see that in fact it does equal 1. For D, I've got tangent squared of 123 plus 1 would have to equal secant squared of 123 degrees. So the moral of the story here is that the angles have to match going all the way across in any Pythagorean identity. So I'm going to take a minute to fill in this box at the top of the next page of your notes with all 3 Pythagorean identities so that I get used to using these Pythagorean identities. I don't actually memorize all 3 of them. I've memorized the first one, cosine squared theta plus sine squared theta equals 1, and then I memorize how to get the other 2, just like we did on the previous page in those 2 boxes, dividing by cosine squared and then dividing by sine squared. So now let's fill in the box with these 3 Pythagorean identities. So you can see the 3 Pythagorean identities are cosine squared theta plus sine squared theta equals 1, 1 plus tangent squared theta equals secant squared theta, and cotangent squared theta plus 1 equals cosecant squared theta. So remember the pairs that go together, and notice that all of the other terms are just 1s. So let's use Pythagorean identities to solve each of the following examples. In example number 2, it says we have an angle theta whose terminal ray falls in the second quadrant. The quadrant is, of course, going to tell us whether our answer is going to turn out positive or negative for that particular function. So in the first example, I've got that the cosine is equal to negative 12 over 13, and I want to find the sine. So that tells me to use the first Pythagorean identity. So I'm going to write down the identity that I am using. So cosine squared theta plus sine squared theta is equal to 1. Replace the cosine with negative 12 over 13. And we've seen examples like this before. We're going to square that value so that then we will be able to solve for the sine of theta. Don't forget the squared. When I square negative 12 over 13, that's giving me 144 over 169 plus the sine of theta squared equals 1. We're going to subtract 144 over 169 from both sides. So I've got 1 minus 144 over 169. Now you can either use your calculator or you can find a common denominator and say that the sine of theta squared is equal to 169 over 169 minus 144 over 169, which of course gives us 25 over 169. To solve this equation for the sine of theta, we're going to take the square root on both sides of the equation, and on the number side, make sure you think about the positive and negative. So I know that the sine of theta, in this case, is going to either be positive or negative 5 over 13. Going back to the idea that I'm in the second quadrant, Think about our quadrants, and in the second quadrant, I know that my x-coordinate is negative, but my y-coordinate is positive. Since sine is the y-coordinate, I'm going to pick the positive answer for this one and say that the sine of theta is equal to positive 5/13. Looking at example number 3, it says an angle theta has a terminal ray that falls in the fourth quadrant. So again, that quadrant is going to be important for our positive or negative. I know that the secant of theta is equal to 5/4, and I want to find the tangent of theta. So pick the appropriate Pythagorean identity. So I'm going to say for this one I have to use 1 plus tangent of theta squared equals secant of theta squared. So that's putting together the correct two trig functions. So this time I'm going to be missing the tangent of theta, and I'm going to replace the secant with 5/4 and square that. I'm going to do two steps in one here, so I'm going to say the tangent of theta squared is equal to 25/16, and then let's subtract 1 from both sides of the equation to move it to the right. So that tells me that the tangent of theta squared is equal to 25/16 minus 16/16, and that's going to give me 9/16. Go ahead and take the square root on both sides of the equation. So in this case, I get that the tangent of theta would be equal to plus or minus, the square root of this is going to be 3/4. Now we've got to look at our quadrant. In the fourth quadrant, I know that my x-coordinate is positive while my y-coordinate is negative. And since tangent is y divided by x, I know that my tangent is going to be negative in that fourth quadrant. So the tangent of theta is going to be negative 3/4 for our answer. Going on to example number 4, the terminal ray of beta lies in the third quadrant. I've got sine of beta is equal to negative 5/7, and I want to find both the cosine of beta and the tangent of beta in simplest form. So let's use the appropriate Pythagorean identity. So cosine of beta squared plus sine of beta squared equals 1. So replace the sine with negative 5/7. So I've got cosine of beta squared plus negative 5/7 squared equals 1. Notice that this makes sense because in the third quadrant, sine would be negative because the y-coordinate is negative there. Cosine of beta squared is equal to, I'm going to subtract right away. So I'm going to have 1 minus, and then subtracting after I've squared, I've got 25/49. Do that subtraction, so cosine of beta squared is equal to 49/49 minus 25/49 gives me 24/49. Square root both sides of this equation, keeping the positive and negative on the number side. So the cosine of beta is equal to plus or minus the square root of 24. I can reduce that radical. It's not a perfect square, but it has a perfect square factor. So that's going to be 2 radical 6 over 7. Now let's pick the correct quadrant, or positive and negative, based on our quadrant. In the third quadrant, I know that my x is negative and my y is positive. Ooh, I'm in the wrong quadrant. Let's try that again. In the third quadrant, I know that my x is negative and my y is negative. So therefore, the cosine has to be negative there. So the answer for cosine of beta is just equal to negative 2 root 6 over 7. So there's one answer. Now, recall that to get tangent, all I'm going to do is say that tangent is equal to sine divided by cosine. So now that I have both of those answers, let's do that division. So the sine is negative 5/7. The cosine is negative 2 root 6 over 7. So let's do that keep change flip. So negative 5/7 multiply by the reciprocal, 7 over negative 2 radical 6. First of all, my 7's would cancel. Secondly, my negatives would cancel. So right now I have 5 over 2 root 6. I don't want to leave a radical in the denominator of my fraction, so I'm going to multiply the top and the bottom by radical 6. So that gives me, for my answer for tangent of beta, I would end up with 5 radical 6 over 2 times 6, which is 12. You'll notice that the signs, positives and negatives, end up working out correctly here when I divide sine by cosine, because in that third quadrant, tangent should turn out positive. Let's go ahead and finish our last example, this time with our trig functions cosecant and cotangent. It says, suppose that the angle theta is between pi over 2. I think by now we all know that pi over 2 is 90 degrees and pi is 180 degrees. So if my angle is between 90 and 180 degrees, that tells me my angle must terminate in quadrant number 2. So that's another way for them to tell me what quadrant I'm in. My Pythagorean identity this time is going to be cotangent theta squared plus 1 equals cosecant of theta squared. Let's replace the cosecant with radical 3, so I'm going to say cotangent of theta squared plus 1 is equal to radical 3 squared. Square that radical 3 and go ahead and subtract the 1 from both sides of the equation. So radical 3 squared gives me a regular 3. Subtract the 1. So the cotangent of theta squared must be equal to 2. Take the square root on both sides of the equation. Don't forget the positive and negative. So now I have that the cotangent of theta should be equal to radical 2. Now let's think right away about our quadrant here. Since I'm in quadrant number 2, my coordinates, my x is negative, my y is positive. The cotangent is equal to the cosine over the sine. Cosine is negative divided by sine is positive, so that tells me that cotangent in quadrant number 2 should be negative. So here's my first answer, cotangent negative radical 2. Now to get the tangent answer, we're going to have to do the reciprocal, so we're going to say 1 over the cotangent. The reciprocals of each other. So the reciprocal of negative radical 2 would be negative 1 over radical 2. I want to rationalize that answer, so I'm going to multiply the top and the bottom by radical 2. So I'm getting for my answer for tangent of theta still negative, negative root 2 over 2. So you can see that these Pythagorean identities are very, very useful in allowing us to solve for missing trig functions when I'm given just information about one of the trig functions, and I'm also given information about what quadrant the angle has to terminate in. So thanks for practicing with the Pythagorean identities. Please familiarize yourself with these 3 identities because we're going to be using those in class, not only tomorrow, but for the rest of the unit. These are really important identities for trigonometry. Have a great night, and we'll see you next time. Bye-bye.